From hydropower to subterranean gravity. A first principles. Analysis of energy storage part. Why? The foundation of power. Harnessing potential energy. The entire mechanism of hydroelectric power and advanced gravity storage is rooted in a single, unyielding physical principle. The conversion of potential energy into kinetic energy, and kinetic energy into electricity. To understand the feasibility of a futuristic deep underground storage system, we must first deconstruct the established benchmark of power generation, the Hoover Dam. Hoover Dam, storing gravity's potential. Hoover Dam functions as the world's most powerful expression of pumped hydro storage, PHS. Physics, using the Earth's gravitational field as a massive battery. Energy is stored as gravitational potential energy, EP. In the water held back by the dam, the amount of energy stored is fundamentally defined by the mass of the water and the vertical height, h, it is allowed to fall. The Hoover Dam creates a maximum operational hydraulic head, the vertical distance the water travels, of approximately 180 meters, 590 feet. This distance dictates the maximum pressure applied to the generating system, 45,000 pounds per square foot at the dam's base. The mechanical conversion process. When electricity is needed, massive pipes called penstocks funnel the high-pressure water from the reservoir down toward the power plant. The system involves a precise kinetic sequence. Turbine. The force of the falling water strikes the blades of a Francis turbine, causing the connected shaft to rotate rapidly. Shaft. The shaft transfers this mechanical, rotational energy directly to the generator assembly. Generator. This mechanical rotation is the input for the final stage. Creating electricity. Part 2. The first principle of electricity, Faraday's law. Conversion of mechanical energy into electrical energy relies entirely on the principle discovered by Michael Faraday in 1831 that electricity can be created by rotating magnets within copper O. Coils. 2.1 Anatomy of the generator. A hydroelectric generator is composed of two primary elements that interact through an induced magnetic field. The rotor, the magnet, a series of electromagnets, also called poles, connected to the rotating shaft. A smaller generator called the exciter creates the electricity that charges the rotor, giving it its magnetic field. The stator, the coil, a stationary, non-moving coil of copper wire that encircles the rotor. Electricity is produced as the magnetic fields of the rotating rotor sweep past the stationary copper wiring of the stator. This process induces an electrical current in the wire, which is then sent through transformers to be distributed onto the power grid. This is the fundamental first principles mechanism of all large-scale electricity generation. Understanding storage metrics. Density and power. Once generated, energy must be stored, which introduces the concepts of density and power, essential for comparing storage technologies like PHS and batteries. Metric definition. First principle. Application energy density, WHKG or WHL. The total amount of energy a system can store per unit of mass or volume determines the duration, how long a device can run, or the capacity, how large the battery is. Power density, WKG, the rate at which a system can deliver energy per unit of mass, determines the instantaneous output, how fast a device can accelerate or how many megawatts a generator can produce. Conventional PHS has an extremely low gravimetric energy density, 0.5 to 3 WKG, while advanced lithium-ion batteries achieve a high gravimetric density, 150-190 WKG. Gravitational storage, therefore, cannot compete on weight, but must compete on longevity and volume. Part 3. Re-engineering gravity, the SGS-CMM. Concept the subterranean gravity storage with centralized moving mass. SGS-CMM is a hypothetical concept that seeks to eliminate the land use issues of PHS, while vastly increasing energy density through the extreme manipulation of pressure and volume. The physics of subterranean buoyancy, unlike the Hoover Dam, which uses a large volume of water moving down a small vertical distance. The SGS-CMM uses a dense, heavy object, the rock or mass, moving inside a water-filled chamber. The storage mechanism is identical to the PHS principle of gravitational potential energy. Charging, storing energy. Electrical energy is used to power a motor pump system that pulls the heavy, central mass up within the spherical chamber, forcing it against the force of gravity. Discharging, generating power. The mass is released, allowing the force of gravity to pull it down. This downward movement is controlled by a high-pressure hydraulic system connected to a reversible pump turbine, RPT, which generates electricity, like the Hoover Dam turbine. The spherical chamber is placed deep underground to leverage the ambient pressure, which stabilizes the structure. By maximizing the density of the central mass compared to the water, the system maximizes the effective submerged weight, requiring a smaller chamber volume to store the same amount of energy, leading to superior volumetric density. This is how it aims to justify the high cost of deep excavation. 2. Engineering constraints. Depth, pressure, and tunnels. The feasibility of SGS-CMM rests on overcoming extreme engineering challenges, pushing limits far beyond established precedents. The pressure tier. The maximum working pressure defines the system's performance. Industrial preparation of high-yield steel surfaces can tolerate pressures up to 20,000 psi, 1379 bar. This material limit determines how deep the spherical chamber can be placed, as water pressure increases by 1 bar for every 10 meters of depth. To ensure long-term integrity over an expected 80-year lifespan, the operational pressure must be well below this maximum tolerance. The excavation challenge. Excavating a massive spherical chamber deep underground is prohibitively expensive using conventional methods. The system relies on the economic feasibility provided by disruptive tunneling technologies, such as those promoted by Elon Musk's ventures. For example, the Boring Company's Proofrock machine aims to reach speeds of 1 mile per week to drastically reduce construction time and cost. This breakthrough in speed and cost is necessary to compete with the established cost of PHS. The turbine scale. The Hoover Dam's Francis turbines operate under a maximum head of 180 meters. The SGS-CMM, operating at depths of 1,000 to 2,000 meters or more, requires RPTs capable of managing hydraulic heads 5 to 10 times greater. This demands the development of bespoke, ultra-high-pressure hydromechanical systems that surpass current established hydropower technology.